Okay, so I'm going to cover recurrence equations and then this kind of what they call a cheat sheet. It's called a master theorem for analyzing the running time of an algorithm that we're using. So we're going to use a sorting algorithm. I know last time we talked about a sorting algorithm that had, we said that the running time was n squared, right? We had an algorithm that said, let's take, assuming that a section of the array was sorted, we pick the next number and then find the spot where it belongs. Then assume the next group is sorted, take the next number and go back, and we call that insertion sort. This is a different sorting algorithm, and it's called merge sort. And what you basically do is you take a random set of numbers and you say, well, I'm going to assume that if the first half was already sorted and the second half was already sorted, then how can we how can we take two sorted lists and make one big sorted list out of them? So what we would do is we would put pointers at the beginning of each one and ask ourselves, assuming this was sorted already, we could say which is smaller, this one or this one? And whichever one is smaller, we write that to the answer and move the pointer up, right? And then have another face-off over and over. So we could say which is bigger out of this and this, and then move that one down. So the array originally starts off not sorted at all. So the way our algorithm works, it says, if this was sorted and this was sorted, then we merge them together. Well, the way we're going to sort this half is to cut it in half. And say if this was sorted and this was sorted, then we can merge these two lists together, and then once that's done, we can merge the outer lists together. So these are not necessarily sorted, so we cut those into separate lists, and it eventually gets to the point where they all get cut down into individual lists. So now we have 2 and 3, and we ask ourselves, out of these two, which one's smaller? And the 2 is smaller, so that gets written here, and then the 3 gets written here. And now we have this list is sorted. And then we say out of 7 and 6, we put pointers at the beginning of each list, even though they're of size 1 right now. And we say which one is smaller out of these two numbers. The 6 gets written down, and then the 7 gets written down. Now this list is sorted. Out of the 8 and the 5 goes first, the 8 goes second. And out of 1 and 4, the 1 goes first, and the 4 goes second. Now what we have to do is take these two lists and merge them into one sorted list. So we put a pointer here and a pointer here. And we say, what's smaller out of 2 and 6? The 2 is smaller, so we write a 2 and then we move the pointer up. Now we say, what's smaller out of 3 and 6? 3 is smaller, so 3 gets written, and now this list is done, and we can write 6 and 7. And now this list and this list were merged into each other. Same thing over here. If we have a 5 and a 1, we ask ourselves which is smaller of these two. The 1 is smaller, so it gets written here, and then we advance to the 4. Now we say, what's smaller, 4 or 5? 4 is smaller, so 4 gets written. And then this one's done. So then a 5 gets written and an 8 gets written. Now we have these two lists. So now at this point, at this level here, we basically have this list sorted, 1, 2, 6, 7, 1, 2, 6, 7, and we have this list sorted, 1, 4, 5, 8. Now we want to take these two lists and merge them together. So we put pointers at the beginning of each, and we say 1 is smaller, so 1 gets copied into the answer, and the pointers are now pointing at 2 and 4. 2 gets written here, the pointer gets advanced. Out of 3 and 4, which is smaller? The 3 is, so that gets written here, and the pointer advances. 4 and 6, which is smaller? 4 gets written. And then this moves up to a 5. Now out of 5 and 6, 5 gets written down. And then we have 6 and 8. 6 gets written. Then 7 gets written. Actually, we lost 8 somewhere. But anyway, you get the idea. The 8 should have been copied here, right? So this algorithm is called the merge sort algorithm. So it's basically taking, the idea is to take two lists that are already sorted and merge them into one big list. So the algorithm, just, the idea of it, it's a recursive algorithm, so that's where you have a function that calls itself. So basically what we're doing is we're taking the range from P to R of the array, dividing it in half, adding the two together, dividing in half. So we're getting a node that's in the middle. And then we're saying take the original array from P up to the middle, and then call merge sort on that one. And then take from Q plus 1, the one right after the middle, to the end, and call merge sort on that half. And then we're going to call another routine, the routine like I was doing with my fingers, where we put the pointers and then just copy the results over. So now, what is the running time of the merge routine? The place where I put my two fingers out and I said, which one is smaller, copy it over, move the pointer. Which one's smaller, right? I kept copying over the smaller ones. How long would that step take? Like how many steps are involved? So if you had n numbers, which means we have two lists, half of n and another half of n, how long would it take until we merge them together? How many steps would be involved?
Just on the merged portion of it, n.
Right, that'd be n steps, because for each node we have to take one step to compare. Basically, the step is compare the two numbers, figure out which one is smaller, copy that one over, and then move the pointer. And that gets done n times. So this step's going to be done n times. How many times will this step get done? Or how much time will each one of these steps take? Now these steps, they're calling the same routine again, but we're calling it with less data. If we kept calling itself with the same data, it would run forever, right? It would go into an infinite loop. So if we wanted to analyze how much time this overall algorithm takes, we can, well, okay, before we do that, we'll take a quick review of logarithms. Because of basically, what you start to see is happening, it's going to be, the amount of time it takes to do a full merge sort is really going to be 2 half sorts plus a time n algorithm. So like if it took an hour to do an overall merge sort, we're really going to be doing 2 half merge sorts. It might take a half hour each and then add those together. So just a little quick review of how logarithms work, because the logarithm is going to come up in this. Like if I asked you to multiply these two numbers together, you might need a calculator to do that. But if I asked you to multiply these two numbers together, you wouldn't need a calculator, because basically the trick we use is we take the number of zeros, add them together, and then put that many zeros over here. But technically what we're doing is we're using logarithms. And we're actually using base 10 logarithms for this particular example. So logarithms have a particular base to them. So for example, what we're really doing is we're saying that the log base 10 of 1,000 is 3, log base 10 of 10,000 is 4, 3 plus 4 is 7, and then we take, the official name is the anti-log, but the reverse of the log is 7, and we get 10 million. And then other logarithms, that it doesn't have to be base 10, it could be base any number. So it's basically an exponent. We're asking ourselves, if we took 10 and raised it to the 7, that would be the reverse log, that would be 10 million. So the log base 10 of 10 million would be 7, and like we have up here, log base 10 of 1,000 is 3, which basically means how many times do we have to multiply 10 together to get to 1,000? So 10 times 10 times 10 is 1,000. So that would be 3. 10 times 10 times 10 times 10. 4 times would be 10,000, and so on. So the most common logarithm used in computer science is base 2. But actually, we're going to look at other bases too when we talk about quicksort in our next class. Okay, so now if we wanted to know how much time it took to run this algorithm, if n for merge sort was of size 1, how long would it take? Well, it would just take one operation. We would look at the number, when we go to split it in half, we realize we're done. So that would be one operation. But if it was greater than 1, how long would it take to run this program? So remember what the program does. It takes the original input, it makes 2 calls to itself, so 2 calls with half as much data, and then it does that merge step, that cleanup step at the end. So how long does it take? Well, we don't know what it takes. T of n means how much time it took if we ran it. But we know one thing. It's going to take however long it takes with half as much data. We're going to do that 2 times. We're going to call merge sort on the first half, which has half as much data, and then we're going to call merge sort on the second half, which also has half as much data. And then we're going to run an algorithm which has a linear running time to it, where we merge the two lists together. So if n is greater than 1, the amount of time it will take is, so let's say for example n is 2. We're going to call merge sort on a list of size 1, merge sort on another list of size 1, and then we're going to merge those two answers together. So the total running time would be 2 times the amount of time it takes if we had half as much data, and then this merging step. So that doesn't really give us an answer, but it just gives us an inductive equation for it. How long does it take, how long does this piece right here take? T of n over 2. Well, T of n over 2 is going to take 2 times T of n over 4, right? The amount of time it takes to do a half a list is 2 times the amount of time it takes to do a quarter of a list, right? Times 2, and then we have to merge that together. So all we're doing here is we're taking this piece, this part right here, and expanding it into this. See, so the n over 2, it's 2 times n over 4 plus, now we're going to clean up 2 half lists, right? Now we could take this equation and kind of just clean it up a little bit. 2 times 2 becomes a 4. The 2, this 2 gets put over here. 2 times n order n over 2 algorithm is really like 1 order n algorithm. So this cleanup step plus the 2 half cleanup steps from the previous level is like 2 cleanup steps. And then if we wanted to take t of n over 4, that's really the same as 2 times t of n over 8 plus the merging of 4 mini lists together. And then we can clean that up, and we end up getting, there's 3 merged layers. So does that make sense that the way it's splitting up, it's like, let me go back to the picture, just to get an idea of how much work is involved. If we went back to this picture, we're going to take the original set of numbers, n, and we're basically saying, how much work does this whole algorithm do? Well, to get this part, we had to call merge sort on this part and merge sort on this part, and then we had to run pointers through these. So the amount of work to run the pointers through was size n. At the level before that, we had to run pointers through this 2 and pointers through this 2, but this whole level took n amount of work. So each level, the merging step takes n amount of work, and now we just want to know how many levels are there. To know how many times do we have to do n amount of work. So this algorithm is basically saying that we had to, by the time we were finally done, this keeps going, this process keeps going, where we cut the number in half and a half and a half, and eventually it runs down to 1. So eventually, the lists got so broken up, they're all size 1. The question is, how many hops were in that picture from before? And it turns out, log base 2, if you take a number and keep cutting it in half until it goes away, it ends up being log base 2. Actually, could have put a log base 2, but in a second we'll see we don't have to worry about the bases when it comes to this big O notation. So what we end up doing for each layer, we kept adding 1 additional amount of n steps for cleanup. So by the time we were done, this thing hit this was n, there were n steps. It started off as 2, then it became 4, then it became 8, then it becomes 16. And each time this number was starting at whatever n was and going in half and a quarter and 8 and so on. So this built up to n. This eventually became 1. So it's n times, that's the point where the algorithm broke up the list all into n size 1 links. So this step is where the n links, which had no sorting to do because an array of size 1 is already sorted. There's no more work to do. That's covered in this step. And then this is how many layers there were and how many times we had to do log n amount of work. So the total amount of time for this algorithm is, there's n steps. That's where we have the list of size 1, and we say, all we have to do is say we're sorted. We don't have to do anything else. And then the number of layers is log n, and at each layer we had n amount of work to do. So the running time of this algorithm is n log n. And it's actually n log base 2 of n, but we'll see in a little while. We don't really care about the bases. And this is a lot better than what we had last time with insertion sort, which was n squared. So if n got really big, like for example, the algorithm we did with insertion sort, if n went from, let's say if n was 1,000, that could take 3 zeros, 6 zeros, that could take 1 million steps. Whereas if this went to 1,000, it would take 1,000 times log of 1,000, which could be something like 2,000 steps, instead of going into millions. So this would be a lot better if n got very large than the one we did last time. Okay. Okay, so this is a pretty common recurrence equation. So what I mean by recurrence equation is whenever you have any routine that makes a call to itself, any sorting routine, or actually any routine we ever do, where we have the amount of time it takes for the algorithm to run is equal to a certain number of calls to itself with less data than it originally had, we're going to end up going through some very long, painful equation like this until we get to the bottom. So a famous person, I guess the last name is Master, came up with what's called the Master's Theorem. And it basically says if you start off with a recurrence equation that has this form, the form of the equation is like this. The time that your algorithm takes to run, your algorithm makes calls to itself with a certain percentage of the original data. And it makes a certain number of calls to it. So last time we had 2 calls with half as much data. But now suppose we wanted to modify the merge sort. Instead of cutting it into 2 lists and merging them together, why not cut into 3 lists, right? That'll still work. So you take your original array, cut it into 3 equal lists, sort those. Now the part where we merge the lists together, we're going to need 3 pointers, right? And then every time we say who's the next smallest number, we'd have to look at all 3, pick the smallest one, move that pointer up, and then look at all 3 again. But that would still work. So that recurrence equation, if we did a merge sort where we split it 3 ways, it would be T of n equals 3 times n over 3. We'd be putting in 1/3 as much data each time. And then the last part would still be that across-the-board merge step, which would take a running time of order n. So really, any time you have an algorithm that calls itself recursively, it has to be calling itself with less data than it used before, otherwise it'll run forever, right? So this is always going to be n divided by something. And then maybe, depending on what your algorithm does, it might have to make many calls. So the question now starts to become, if A is small and B is big, this thing will go away very quickly, and this term, whatever this term is, could be the dominating thing. If A is very large, and there's many, many calls to itself, then this part could be the dominating term. So this is just a little cheat sheet. If you ever are given the running time for a recursive algorithm, and it's of the form a certain number of calls to itself with a percentage of the original data, and then some cleanup step after it, like we did with merge sort, we had to clean up the result. We could say to ourselves, there's 3 different cases. We could have the case where the f of n, which is this thing out here, which had the running time, like for merge sort, had the running time of order n. if this is running time is equal to big O of n to the log, there's a b here, log b of a minus some epsilon, for some epsilon greater than 0, then the answer will end up being the running time of the overall algorithm is n to the log b of a. We'll go over examples shortly. So this would be where one term is dominating the other. If the f of n, this part, is exactly equal to theta of n to the log b of a, then the recurrence equation is theta log b of a log n. Like I said, we'll go over an example of this. The last case of the Masses theorem is if the f of n, this function over here, is omega n to the log b of a plus some epsilon, and epsilon greater than 0. And also if f of n over b is less than some constant c of f of n, for some constant less than 1 for sufficiently large n, then the answer ends up being whatever this term is. That means this term ended up dominating the whole algorithm. Okay, so I know this is like it's a cheat sheet for when you're given a recurrence equation, and hopefully you could try some of these examples, and if they work, so for example, suppose we had an algorithm that said the running time is equal to 9 times the running time if you gave the algorithm 1/3 of the data plus n steps. So first of all, just to kind of make sure we know what we're talking about, what does it look like is happening here? Whatever the algorithm is we're analyzing, it seems to be making 9 calls to itself. And each call uses 1/3 the original data. I don't know what this algorithm's doing, but that's what it looks like, right? And then when that step is done, it has some other step that runs and has n steps too. So using the Masses theorem, we could say that a is equal to 9, b is equal to 3, and f of n is equal to n. So here's a, here's b, and whatever is added on over here is your f of n. Since n to the log 3 of 9 is equal to n squared, by letting e equal 1, we can apply case 1 so that the running time of the algorithm is equal to log base 3 of 9, which is n squared. So case 1 was this. Okay, so wait, first of all, n to the log 3 of 9. Log base 3 of 9 is 2, right? 3 times 3. How many times do we have to multiply 3 together to get to 9? So log base 3 of 9 is a 2. Since log base 3 of 9, which is really equal to n squared, we could let the e number equal 1. So let me just go back and...
Excuse me.
Yeah?
Did you say log base 3 of 9?
Log base 3 of 9. So, yeah, so what we're doing is this. The way this Masses theorem works is you're given a recurrence equation, there'll be a number here, that's basically how many times you called yourself. This number, the b, that's how much of a reduction in the input you're sending into each call. And then this could be anything, whatever your algorithm does, whatever cleanup it does at the end of these recursive calls. This could be, this could be a function like n squared, n cubed, or constant time, it could be anything. So what the Masses theorem is asking you to do is basically take n to the log of b of a, so n to the log base 3 of 9, and compare that to this. And if one dominates the other, that tells you which version of the Masses theorem to use. So what we're doing is we're saying log base n to the log base 3 of 9 is exactly equal to n squared. So now we're asking ourselves, where does that fit into the Masses theorem? And the Masses theorem says, the master theorem says, so the master theorem case 1 is basically saying this. If f of n is dominated by n to the log b of a minus some epsilon. So the thing is this, in our case, n to the log 9 base 3 was equal to 2. We can let epsilon be a 1, right? We get to subtract 1. So in other words, the power of this thing ended up being bigger than the function we had. We had an n of 1. So does that make sense? There are cases where it's going to match it exactly. If we had a case where it was 9 with 1/3 of the input going in and then plus n squared, it would have matched exactly. But in this case, it ended up being log base 3 of 9 ended up being greater than what the power of our n was. So it might have been a little less confusing if the example was a case 2 example. But we'll go to a case 2 example in a second. So basically what we're saying is log base 3 of 9 is 2. The function over here is less than n squared. So that put us in case 1. Yeah, so that put us in case 1. If, for example, well, we'll do case 3-1 in a second, but does it make sense that we're in case 1? Yeah?
Epsilon always has to be an integer in this case?
No.
We're dealing with, okay.
It could be a fraction, but it has to be positive.
Okay.
So, for example, if this was n squared, then what would happen? Log base b of a would have been a 2, and it would have perfectly matched this thing. This would have been an n squared. So in that case, we'd be in case 2. Case 2 is where they're equal. And case, right? So, for example, if the function was 9 and n divided by 3, and this function out here was n squared, then they would have matched perfectly, right? We would have had n to the base 3 of 9, which is exactly the same as n squared, would have perfectly matched n squared if this was out here. So if our function was 9 t of n divided by 3 plus n squared, we would be perfectly in case 2. That makes, maybe what I should have done was I should have had a case 2 example, which hit perfectly, and then the case 1 and 3 are where they don't hit perfectly, and we either subtract an epsilon or add an epsilon to make it work. So yeah, the case that would have worked perfectly would be case 2. So yeah,
If I look at 1 and 2 up there,
right.
everything we're saying, we're using an equal, not a greater than. Everything is based upon an equal.
Well, okay. I'm thinking it might be the best thing to, if I go over an example like this. If we had t of n equals 9 t of n over 3 plus n squared. If this was our recurrence equation, right, let's say this was, okay, and our algorithm is basically calling itself 9 times. Every pass it calls itself 9 times, but it sends in 1/3 of the original data. Then, after those 9 calls are made, it does something that has a running time of n squared. What we're going to always do is we're going to compare this function, which is n squared, to this function, n raised to the log base b of a, and see how they compare. Which one is bigger than the other, or are they exactly equal?
So your cases are effectively, one side is greater than, equal to, or less than.
Right.
That's
Case 2 is when they're equal. Right. So really, if you think about it, we're taking this function, putting it here, and then taking this number, and creating this function, and then comparing the two. And asking ourselves, are they equal, or does one dominate the other one? So if this was our equation, we would end up with, we would have n to the log 3 of 9, and compare that to just copying this directly down, n squared, and it turns out they would have matched perfectly. It would be n squared equals n squared. That would be case 2. If this number was, if what we got out here was a little bit lower, n to the 1, then we would have to add something to it. So now what we're saying, case 1 was where log base b of a minus some epsilon. We have to lower this 2 to make it equal that one. So it's basically saying this term dominates this term. The third case was when we had to add an epsilon, which said that this term dominated this term. And the second case was when they were perfectly equal. So, yeah, that's probably a better way to explain it. So then if, so let me bring back the case. And, okay, so basically, the way the Master's Theorem is saying is basically, if you ever have an equation like this, we have a number of recursive calls, the thing that's dividing the input to get it smaller and smaller, so your algorithm eventually ends, and then, depending on whatever your algorithm does, you have some freedom to do some kind of computation after that. We're going to do a comparison of n to the log b of a, and see how that compares to whatever this is. Case 2 ends up being where they match exactly. Case 1 ends up being where this term is bigger than this term. So we have to do a minus epsilon to make them equal. But that's basically, this minus epsilon is really like saying this term dominates this term. Case 3 is not perfectly saying that the first term dominates the second one because we had to add an epsilon to make them equal. There also has to be another special case. So there's actually one case where this Master's Theorem won't work. So it's really like, case 2 is when they're equal. Case 1 is when the first term, the n to the log b of a dominates the f function. And we had to actually do a minus epsilon to make them equal. That's the first case, and then the third case is where the function dominates the n to the log b of a term. Yeah?
Well, the thing I'm looking at is that in number 1,
Right.
you have big O, the other, number 2, you have theta.
Right, that's both
3,
ways,
right?
is
And
omega.
the other one less than the omega.
Right.
So
If you remember the big O from last class, the big O is saying this term will always dominate the one before it. the theta says that this term will always be dominated by the one before. And then when they match perfectly, we could use this symbol. Okay, so back to one of the example was, the first one, we had a 9 at 3 and the function ended up being n. So we're comparing, we're going to build n to the log 3, n to the log base 3 of 9, which is n squared. N squared beats n, is greater than n when n gets very large. Therefore, we're in case 1. Case 1 tells us that we should use n to the log b of n squared, n to the log 3 of 9. So the running time of this algorithm, just using this cheat sheet to get our answer, would be n squared. We don't have to go any further. So we just look at this, we realize we're in case 1, and the cheat sheet tells us the answer. The second one, t of n equals, this looks like an algorithm that takes, every time you call the algorithm, it calls itself with 2/3 of the original input. And then it does some constant time operation, one step after it's done. So here we have an a of 1, a b of 3/2, and the f of n function is this thing out here, which is just 1. So log of base 3/2 of 1 ends up being 0, and n to the 0 is equal to 1. So that puts us in case 2. So in this case, case 2 applies, and case 2 told us to make it n to the log base b of a, which is a 1, and it said it was actually n to the log base b of a times log n, was what it said on the cheat sheet. So I'll just bring the sheet back up. This basically said if we are in case 2, then the running time of the algorithm is n to the log b of a times log n. So in that case, it ended up being, this was a 1, so it would be 1 times log n. So that ended up being log n. And then the third case, an example of the third case is where we have the recurrence equation is, this looks like the algorithm is calling itself 3 times, but giving 1/4 of the data. So apparently it's 1/4 of the data it doesn't care about. So whatever it's trying to solve, maybe after looking at 3/4 of the data, it can throw away 1/4. Then, after those 3 calls are made, it has some n log n step coming after it. So, our a is 3, our b is 4, and our f of n, the part out here, is n log n. If we put it in case 3, we realize that n to the log base 4 of 3 is approximately n to the 0.08. It's not quite 1, which means we'd have to add an epsilon of 0.02 to get it to equal. And then the t of n has the running time of f of n, and a f of n over 2 equals 3 times 1/4 n log 1/4 of n. That is less than 3/4 of n log n, so that second condition ends up being true. And that means we're put in case 3. And therefore, the cheat sheet tells us that the answer is always, what does that tell us? The cheat sheet tells us the answer, once you're in case 3, the answer is f of n. So the f of n term ends up being the dominating term. So this is basically saying if you find yourself in case 3, this term ends up being the dominating term, and that's the running time of the algorithm. So because we proved that we were in case 3, the running time of the algorithm was n log n. So yeah, so the cheat sheet tells us that. Then the fourth example is one where the master's theorem doesn't apply. So again, there's three cases. There's case one. One is where n to the base of 3, I'm sorry, log base 3 of 9 was bigger than this function. That's case one, and the cheat sheet tells us what the answer is. Case two is where they equal each other perfectly. Cheat sheet tells us the answer. Case three, we have to meet two conditions. This term has to dominate this term, and then in addition to that, that second condition that n over b is less than or equal to a value c that we had to pick up. So we had to meet the second condition. This fourth example is one where the master's theorem won't work. So we take our recurrence equation, t of n equals 2t of n over 2. That looks like we're calling ourselves twice with half as much data. And then we have some n log n step after that, maybe some sorting step after that. So here a is 2, b is 2, and f of n is n log n. It looks like we can come up with a small enough e to make this formula come true. So we can make this come true if we have a small enough e. But then since n to the log 2 of 2 is equal to n, right, log base 2 of 2 is 1. So n to the, since these equal each other, we need to find a positive epsilon such that n to the e is asymptotically larger than log n, but there is no such epsilon. So in this case, we can make that second part of the third condition come true. So we can't really use the master's theorem in this case. We'd still have to solve the question by plugging, where we see this t of n over 2, we'd have to plug this whole equation back into it, and like we did before, iteratively just keep going until we hit the bottom and do it, solve it that way. So what these examples are is, these are examples of, I think that's the end, yeah. These are examples of where our recurrence equation is, the time it takes for our algorithm to run is it keeps making calls to itself, but the calls keep getting smaller and smaller with the amount of input. But maybe the number of times it gets called could be growing. And then there might be some function that happens after these calls are made to somehow tidy up the answers. And we're basically trying to figure out from that equation what's the overall running time of the algorithm. So a lot of times this cheat sheet helps and sometimes it doesn't. And we just went over the master's theorem as one example, just to get an idea of what a recurrence equation is.